Somewhere out there is a stretch of concrete highway, built perfectly, inspected, approved, opened to traffic, and slowly, invisibly, being eaten alive from the inside by a chemical reaction happening inside its own rock. Engineers have a nickname for it: concrete cancer. Today, we're opening up the recipe for road concrete and meeting the ingredient that can secretly betray it. Concrete sounds like one material, but it's really a team of four: cement, the glue; aggregate, sand and crushed stone, the bulk filler and structural skeleton; water, which triggers the chemical reaction that hardens everything; and admixtures and additions, the specialists brought in to fine-tune performance. Cement is the real magic. Mix it with water and it doesn't just dry out. It undergoes a chemical reaction called hydration, growing microscopic crystal structures that lock the whole mixture into a solid, interlocking matrix. It's less like glue drying and more like a slow-motion crystal garden growing around every grain of stone. Aggregate makes up the majority of concrete's volume, usually somewhere around 3/4 of it. Its job is mostly mechanical: provide bulk, provide strength, and keep costs down, since aggregate is far cheaper than cement. But, and this is the plot twist of the whole video, aggregate isn't always the passive, boring ingredient everyone assumes it is. Then there's water. Simple enough. It reacts with the cement. But the ratio of water to cement is one of the single most important numbers in all of concrete engineering. Too much water and you get a weaker, more porous concrete, riddled with tiny capillary channels. Too little and the mix becomes unworkable, impossible to properly place and compact. Finally, admixtures and additions. Chemical or mineral ingredients added in small quantities to change how concrete behaves, without changing the basic recipe outline. Some make the wet mix flow more easily without adding water. Some slow down or speed up setting time. And some, as we'll see, are added specifically as a defense mechanism. So what does a road actually demand from this mixture? Road concrete isn't decorative. It takes a beating. Every mix has to be engineered against a checklist of specific threats. First, strength. A road slab needs enough compressive strength to carry truck axle loads for decades without crushing or fatiguing, and enough flexural strength to resist the bending stresses that happen every time a wheel rolls across a joint. Second, workability. Sounds boring, but it's critical. The wet concrete has to be fluid enough to be placed, spread, and compacted properly on site before it starts hardening, without being so watery that it weakens the final product. Third, durability against freeze-thaw cycling. Concrete is porous at a microscopic level, and water sitting in those pores will freeze in winter, expand by about 9%, and physically pry the material apart from the inside. Cycle after cycle, year after year, until the surface starts flaking away. The clever fix for freeze-thaw damage is almost invisible. Air entraining. Admixtures deliberately whip millions of microscopic air bubbles into the wet concrete. When trapped water inside the material freezes and expands, it has somewhere to go, into those tiny air pockets, instead of cracking the surrounding concrete apart. Fourth, skid resistance and surface texture, so tires can actually grip the road in the rain. And fifth, low permeability, keeping aggressive substances like de-icing salts from soaking deep into the slab and attacking the steel reinforcement hidden inside. Meet all 5 of those demands, and you've got yourself a solid, road-ready concrete mix. Which brings us back to that boring, passive ingredient from earlier: aggregate, and the twist nobody sees coming. Remember, aggregate is just crushed rock, and rock, chemically speaking, is not inert. Some rock types, certain forms of quartz, chert, opal, or volcanic glass, contain a specific mineral structure, reactive silica. Meanwhile, cement contains alkalis, sodium and potassium compounds, as a natural byproduct of how cement itself is manufactured. Normally, these alkalis just sit quietly inside the hardened concrete, doing nothing dramatic. But introduce moisture. And any road is guaranteed to have moisture, and those alkalis can start reacting directly with the reactive silica in the aggregate. This is the alkali-silica reaction, or ASR, and the product of that reaction is a gel. Here's where it gets nasty. That gel absorbs water and swells. Trapped deep inside a solid concrete slab with nowhere to expand into, the swelling gel generates enormous internal pressure, enough to physically crack the concrete from the inside out, one aggregate particle at a time. The damage doesn't show up overnight. ASR is a slow-motion process, often taking years or even decades to become visible. And when it finally does surface, it leaves unmistakable fingerprints. The most telltale sign is map cracking, a spiderweb pattern of fine, interconnected cracks spreading across the surface, because the swelling is happening more or less randomly throughout the entire slab at once, not from a single external stress point. Sometimes you'll also see gel actually oozing out through the cracks and hardening on the surface, or small cone-shaped chunks of surface popping out entirely, called pop-outs, where a reactive particle right near the surface expanded and blew its lid. So if this reaction is baked into the chemistry of the ingredients themselves, how do engineers stop concrete from quietly destroying itself for the next 30 years? The good news, ASR is entirely preventable. If you catch it before construction, not after. Defense number 1. Test the aggregate source before you ever build with it. Standardized lab tests can identify whether a particular quarry's stone contains reactive silica minerals, essentially screening candidates before they're allowed anywhere near a road mix. Defense number 2. Use low-alkali cement. If the alkalis simply aren't present in large enough quantities to begin with, the reaction has far less fuel to work with, even if the aggregate is somewhat reactive. Defense number 3, and this is the elegant one. Partially replace ordinary cement with supplementary materials like fly ash or ground granulated blast furnace slag. These byproduct materials chemically bind up free alkalis and reactive silica in a slower, more controlled, non-expansive way, essentially diffusing the reaction before it can build dangerous internal pressure. As a bonus, this also happens to reduce concrete's carbon footprint. Defense number 4. Limit moisture exposure where practical, since ASR needs water to proceed. Materiali water to proceeding. Though, for something that sits outdoors and gets rained on for 30 years, this is more of a supporting strategy than a primary one. Put it all together, and building durable road concrete is really an exercise in interrogating every single ingredient, not just for strength today, but for how it behaves chemically decades from now, in freezing winters, in the rain, under millions of truck axles. So next time you see fine spiderweb cracking on an old concrete road, you're not just looking at wear and tear. You might be looking at a slow chemical reaction that started the day the concrete was poured, quietly playing out one grain of sand at a time.